This is part 8 on topic 4 on defects and strengthening in metals. And in this topic we're going to talk about what happens when we have a solid solution that has too many impurities in it and forms a second phase. And can we use that second phase to our advantage to make a metal stronger? And the answer is yes, we can. Let's get started. So remember, when we finished talking about solid solution strengthening in part 7, our focus was on adding impurities that block dislocations. But what happens if we add too many impurities? Well, for one thing, we change the solidification behavior of the metal. What that means is we actually change the melting temperature and the way in which a material melts or solidifies upon casting. We won't talk too much about this, but it is an important thing to be aware of. But there's also, and more importantly, there's also a limit on how many impurities we can add to the alloy. And that means that if we add too many impurities, we get a precipitate. Just like when we add too much salt to water, we get excess salt. If we add too many impurities into the liquid metal, we'll get too many impurities that come out of solution and form a precipitate. And this can also happen in the solid state. If we have too many impurities in the solid state and we cool the metal down from a high temperature to a lower temperature, you can actually form a solid precipitate within another solid. This is called solid state precipitation. So we're going to look at how we use that precipitate to help improve the strength of the alloy. Before we do that, let's take a look at something called a binary phase diagram, or an equilibrium binary phase diagram. You'll learn more about this in your textbook and also in the online module that's available on PolyLearn, but I want to go over some of the details with you today. This is a binary phase diagram for lead-tin alloys. So lead has the atomic elemental symbol Pb, and tin is Sn, which stands for stannous. And on this diagram, on the x-axis, we have the composition of a lead-tin alloy in percent tin, in weight percent tin. So you notice, for example, if I'm here where the cursor is, that would be a 20 weight percent tin alloy, and the remaining 80 weight percent tin would be lead. If I'm all the way over on the left-hand axis, that's 0% tin, which is the same thing as saying pure lead, which is why we have lead written down here in the lower left corner. Conversely, if I'm over here on the far right-hand side of the diagram, then I have 100% tin and 0% lead, so that's pure tin. And in between you have an alloy of lead and tin. On the y-axis we have temperature. In this case, on the left we have temperature in degrees Celsius, and on the right we have temperature in degrees Fahrenheit. And on the top axis, along the top x-axis, we have composition of tin in atomic percent. So if we counted up the number of atoms, this would be how many tin atoms and how many lead atoms. Since tin and lead have different atomic weights, or atomic masses, the atomic percent tin and the weight percent tin don't exactly line up. We're going to focus on only using the weight percent tin in this class. Now, on the diagram you see you have a series of, or a group of lines, and these lines are called phase boundaries, and they separate phase fields on the diagram. So at very high temperatures we see we have the liquid phase present. So no matter, as long as you're above, let's say 183 degrees Celsius at 61.9 weight percent tin, you'll have liquid phase. But as I go to lower and lower amounts of tin, I have to go to higher and higher temperatures to have all liquid, all the way up to the melting point of pure lead, which is 327 degrees Celsius. Conversely, if I have pure tin, the melting temperature of tin is 232 degrees Celsius. And there's a almost perfectly straight line between 61.9% tin and 100% tin for the melting temperature of that alloy. So pure, I have completely liquid, 100% liquid at these high temperatures. There's also a region where I have 100% alpha phase. Alpha represents the crystal structure of pure lead, but with tin impurities in it. And we can have up to 18.3% tin impurities in that alpha lead. There's also a beta phase way over here on the far right, a small sliver, where I can have the tin crystal structure with lead impurities in it. And I can have up to 2.2% lead, that's 97.8 from subtracted from 100, up to 2.2 weight percent lead in that beta phase field as impurities. Now in addition, there are multiple phase field regions. So for example, I have an alpha plus liquid region where I have both solid alpha and liquid present at the same time. I can have beta plus liquid present at the same time. And I can have alpha and beta, both solids, present at the same time. And just in case it wasn't clear, whenever I have a Greek letter, that represents a solid phase. We also have, as I've already mentioned, a couple of points drawn on here. So here at 18.3 weight percent tin and 183 degrees Celsius, you have alpha, liquid, and beta all present at the same time. At 61.9 weight percent and 183 degrees Celsius, you have liquid, alpha, and beta present. And again, at 97.8% exactly and 183 degrees Celsius, you have alpha, beta, and liquid present. Now, we're not going to cover everything we can do with these diagrams, but I want to go over a few of the basics so you understand how microstructures develop as they cool from a liquid state down to the solid state. One thing you have to keep in mind is this is an equilibrium phase diagram, which means that everything that happens on this diagram occurs at thermodynamic equilibrium. In order for that to happen, we have to have sufficient time for the atoms to rearrange into the crystal structures that have the lowest energy state. Well, giving them time means doing everything very, very, very slowly. So we're going to assume that any changes in temperature that we do on the diagram occur at an infinitely slow rate, which of course is not very realistic, but is close enough to reality that it works pretty well for most applications. So let's begin with an example, and we're going to look at the solidification of a simple solid solution, which we talked about in the last part of these video lectures. So imagine a 1.5 weight percent tin alloy. So what I've done is I've taken the left side of the phase diagram and blown it up so that you can see where 1.5 weight percent tin is. That's the dashed line. And we're going to assume we start at around 380 degrees Celsius here at point A. And we're going to cool from that point A down to room temperature, which is way down here, down near the x-axis, very slowly. So notice that it says very slowly. So we assume that everything stays in equilibrium. So what happens at point A? Well, at point A we have all liquid. Now importantly, we could answer a few more questions about our material. For example, what is the composition of the liquid at A? Well, the composition is 1.5 weight percent tin and 98.5 weight percent lead. What's the mass fraction of liquid? Well, mass fraction means how much phase do we have? Well, we only have one phase, so the mass fraction is 100% liquid. And we can also ask, what does a structure look like? And a liquid simply looks like a flat surface. Some people like to draw waves on their pictures, but there wouldn't even be waves really in a molten metal. So we just have this flat picture of liquid, and that's sufficient for this class. Now let's imagine we cool the material down to point B, where we're between the line for liquid to alpha plus liquid and the line for alpha plus liquid to alpha. By the way, these lines have names. This line at the top between the liquid phase and the alpha plus liquid phase is called the liquidus, and it represents the line at which the first solid begins to form upon cooling. The line down here between the alpha plus liquid and the alpha phase is called the solidus, and it represents the temperature at which all the liquid disappears when cooling. So if we're at point B, we're inside the alpha plus liquid phase field. So what do we see? Well, we see alpha and liquid. We see chunks of solid floating in a liquid phase. Now, we could ask ourselves, what's the composition of the liquid and solid? And they're going to be different because we're in a two-phase field. And for that, we need to use what's called a tie line, which is a parallel line that connects one side of the phase field to the other side of the phase field. You can learn more about this by looking at the online video tutorial that's posted on PolyLearn, and by looking in your textbook. I'm not going to cover it here. But bottom line is the composition of the liquid is higher because we go to the liquidus line to find that composition and then come straight down. And the composition of the solid is less than 1.5 because we go to the solidus line and then come straight down to look that up. We can also talk about the mass fractions. So we have a certain percentage of alpha and a certain percentage of liquid, and those two percentages have to add up to 100% because there's two phases. So what's the percentage of solid alpha and what's the percentage of liquid? And again, that's something you can learn from the tutorials, and I'll encourage you to look at those. They will be part of your homework and probably on the final exam. Now what happens if we cool it all the way down to, say, 100 degrees Celsius? Well, at that point we have all alpha. And we have to draw in little grain boundaries because we had separate chunks of alpha growing, and each of those separate chunks will have a different crystalline orientation, so that as they completely grow and replace all the liquid, eventually the orientations will bump into each other and we get grain boundaries. So that's it. That's what happens as we cool a solid solution down from a liquid state down to the solid state. Now let's take a little bit more complicated case, solid state precipitation. So now consider a 12 weight % tin alloy that's cooled from 350 degrees Celsius to room temperature very slowly. So 12% moves us over to the right on the phase diagram. So here we have our dashed line again, and we're going to cool it from point D, up here where we have molten liquid, to point E, where we have a combination of alpha and liquid, so we would draw a picture with chunks of alpha floating in a liquid, to point F, where we have an alpha solid solution, where we would draw alpha grain boundaries, just as we saw in the last example, to point G. Now point G is special because we've now exceeded this curved line. This curved line where I have the cursor going right now is called the solvus line. And the solvus line represents how many impurities we can dissolve into the alpha phase without forming a new precipitate. Once we cross that phase, that line, that solvus line, we now have no choice but to create a new precipitate, and that precipitate is called the beta phase. So at point G, we're going to have alpha present, but we're also going to have beta precipitates. So what will that look like? It looks something like this. We have alpha grain boundaries, which formed at point F, but now we also have to show the beta precipitates forming throughout the material. Now notice that I've drawn the beta precipitates forming along the grain boundaries. And the reason for this is that the grain boundaries represent an area of disorder. And an area of disorder will have a higher energy state than the low energy crystalline structure within the grains. So therefore, the beta precipitate will choose to grow at a place of high disorder or high energy in order to reduce the energy of the overall system. So typically the precipitates will form at the grain boundaries. A word quickly about phases and grains. It's possible to have one phase and many grains, as shown in the picture on the left. And we've talked about examples of this, like brass, for example. But it's also possible to have two phases and many grains of each of those two phases. So the picture on the right shows two phases, the blue and the green, but I have grains of green and I have grains of blue. And sometimes I have grain boundaries between the blue, and sometimes I have grain boundaries between the green phase, and sometimes I have phase interfaces between the green and the blue. So it gets complicated when you have more than one phase to keep track of what's a grain boundary and what's a phase interface, what's a phase, and what's a grain. So hopefully you'll be able to keep track of that. Now, why do we care about these second phases? What do they do for us? Well, it's important to recognize that a different phase is a different way of organizing matter. So for example, here we have a second phase that has precipitated inside of a different crystal. So here's the host phase out here, and you can see the regular alignment of all the atoms. You can also see a second phase in here which has a different way of organizing the atoms in space. This picture, by the way, is taken by a high-resolution scanning tunneling electron microscope. So this is a very powerful high magnification picture. Now, there's a border that surrounds this phase called the phase interface. And what's important to notice is that where the phase interface exists, there's a darkening in the host phase. And that darkening is what we call strain caused by lattice mismatch. In other words, the atoms in the host material, their bonds are being stretched or compressed in order to accommodate this second phase with the different structure. Now that lattice strain is important because if a dislocation were to travel close to that lattice strain, it would get blocked. And as you know, anytime we block a dislocation, we tend to increase the strength of that material. So that brings us to our final strengthening mechanism, a dispersed secondary phase, or what's also known as precipitation strengthening. And this is very common in industry. The idea is this. If I have secondary phase or particles present, precipitates present in the material, as a dislocation moves along, that dislocation line gets blocked by the precipitate. In order to keep moving, that dislocation has to bow out between the precipitates, much like you would have a balloon bulge out past your fingers if you held it in your hand and blew it up at the same time. Well, you'd have to keep blowing harder and harder and harder in order to keep that dislocation moving. And so the metal appears to be stronger. Now, we don't have grain boundaries here. What we have are phase interfaces that are blocking those dislocations. One of the tricks to this is to have those precipitates be as close to each other as possible. The closer they are, the better they're going to block that dislocation and make it harder for the dislocation to move. So the goal then is to have very small precipitates that are very closely packed together. How can we do that? Well, that's where precipitation heat treatment comes in. And here's how it works. Imagine we have a phase diagram. In this case, it's for aluminum with impurities of copper added. And we're going to add around 4% copper into our aluminum alloy. And this is exactly what we do for an alloy called 2024 aluminum that's used for making bicycle frames. So start out with the aluminum alloy at a high temperature of around 550 degrees Celsius. That'll bring it into the alpha solid solution phase. That's called the solution heat treatment and is represented by this temperature T0. Now imagine we quench that temperature rapidly down to room temperature. So that's the quenching step shown here between points 1 and point 2. From point 1 to point 2, the crystal structure goes from alpha to alpha. But the difference is that you have a supersaturated solution of alpha. Why do you have the supersaturated solution? Because you've quenched it so rapidly that you prevented time for the atoms to move and precipitate to form this theta phase. You can see that now that we're down at point 2, we should have alpha plus theta. But that rapid quenching prevented the theta phase from precipitating out. So now the material is very unstable and at a very high energy state and wants to transform. So what we do is a second heat treatment called the precipitation heat treatment that's at a low temperature. Now that low temperature provides just enough thermal energy to allow the atoms to move around within the host material and form the theta phase precipitate. But the energy is so low the atoms can't move very far, and the result is that the theta phase precipitates are small and widely distributed, which is exactly what we want to maximize the blocking of dislocations and give us the strongest alloy possible. So there's step 1, the solution heat treatment, from stage 1 to 2. There's point 2, the quenching, and there's point 3, the precipitation heat treatment. So what effect does all this have on properties? Well, first let's look at the strength of a material, an aluminum, versus its ductility. So here's pure aluminum, and you notice pure aluminum is very ductile but has very low strength. So one thing I could do is simply add impurities, and that will increase the strength. These are called non-heat treatable alloys, the 3000 and 5000 series aluminum alloys. These are used for things like soda cans. You notice what happens is that while I do get an increase in strength by adding impurities, I lose some ductility. Another approach is to have the heat treatable or precipitation strengthened alloys. These include the 2000 series alloys like 2024, the 6000 series alloys, and the 7000 series alloys. These are all heat treatable alloys. Now, in solid solution strengthening, I'm getting an increase in strength but a reduction in ductility. But notice that the increase in strength is not as great as if I were to use precipitation strengthening. So I can get much better strength enhancement from precipitation strengthening in aluminum alloys, but I have to be aware that I'm losing ductility at the same time. So let's go back to our diagram where we talked about bicycle frames. We compared yield strength to density for a number of materials that might be used for bike frames. So notice here are our aluminum alloys, and what we really mean by the aluminum alloys are the heat treatable aluminum alloys that have low density of around 2.7 grams per cubic centimeter and still reasonably high strength. In fact, the strength of some of the best aluminum alloys are close to that of steel, and yet they're much lighter weight, which is exactly why they're used so commonly in bike frames. And aluminum is relatively inexpensive. Not quite as cheap as steel, but still fairly inexpensive, and certainly much cheaper than magnesium or carbon fiber composite bike frames. Notice, by the way, magnesium bike frames aren't very common, and the reason for that is that they're more expensive than aluminum and really don't give